In the mid-80s, when the first ultrasound machines came on the market which had color Doppler, most people actually thought it was a useless technology and that it will not have a great impact in echocardiography. Well, the reason was that the quality of the color Doppler spectrum was not very good. That has changed, and nowadays there is no way we can perform echocardiography without using color Doppler. In reality, color Doppler is derived from spectral Doppler. Imagine that we have a certain region of interest here, and that in this region of interest we have little areas with spectral Doppler tracings, but these spectral Doppler tracings are encoded in color, depending on which direction and also what the velocity of the blood flow in this region is. And then we get an entire area where we can actually visualize the flow of blood. And how is color encoded? Well, this is pretty much standardized. The first standard is that we have flow which is directed towards the transducer, always in shades of red, while flow away from the transducer is displayed in blue. But then we can also determine how high the velocity is depending on which shading of red we have. And the lighter the red gets, the higher the velocity is. The lighter the blue gets, the lower the velocity is away from the transducer. Now, beyond these conventional rules, there is still a very high variability of how color flow can be displayed. And each machine, each vendor, has several different maps that one can use and display color. So in a way, you always have to get used to how flow looks on a certain machine. One thing, however, which is very important is that each of these maps also has an upper limit. This is the so-called aliasing limit. Remember, in the chapter on Doppler, we talked about the importance of the aliasing limit, the Nyquist limit. Well, this limit is displayed also on the screen. And what happens if the velocity is above this upper limit, the Nyquist limit? Well, then we have the same problem we have with spectral Doppler. We have aliasing. And what happens to the color in this case? Well, take a look at this figure. Imagine we have flow towards the transducer. Now, this flow will be displayed in red. And this flow is below 0.67, which is the Nyquist limit. Then we have no problem in determining also the direction of flow, it's red. But then, if we reach the Nyquist limit, all of a sudden we have a problem in determining the direction of flow, and the color will now turn to blue. So we have a rapid change in color from red to blue, or vice versa, if the flow goes in the other direction. So this is the aliasing border, and this is what happens also in jets which have a velocity above the aliasing limit. Take a look at this jet here. We have red, which would mean flow towards the transducer, and then all of a sudden the velocity gets so high in here that we lose the sense of direction and we have aliasing. Usually the typical pattern of aliasing is that of a mosaic kind of a color map where you have all different shades and colors within this jet. Now, in color Doppler, this is not really a problem. As a matter of fact, it's quite useful because with the help of aliasing, we can really delineate the shape and the size of a jet. However, you have to be aware that we can change the Nyquist limit on the machine. And depending on the setting, your color Doppler, and in particular, your jets will look completely different. Here's an example. We're trying to find a pulmonic regurgitation jet. In this case, we don't see any jet. Why? Because the PRF is very, very low. In this case, all we see is a bunch of colors, aliased colors, and no delineated jet. Now we'll increase the PRF to 0.36, and now we're starting to see a jet here. But still, we have much too much aliasing, many colors in here, all shades of red, blue, and even green. Now we'll increase the velocity of the PRF to 0.54, and now we can really see the jet. Now this is optimal because we can really see that there are different flow velocities within the jet. The center of the jet has a higher velocity than the boundaries of the jet. And we also see that the forward flow here has different velocities as well. Now we change the PRF to 0.90, and we're losing some information about the velocity, but still we can see the jet. And in summary, again, all of the 4 different settings on one slide PRF setting much too low, still too low, probably optimal, and too high. The Nyquist limit you image with is usually defined in your presets. I would recommend you not to change those presets too frequently because you have to get used to your machine. However, there will be situations where it's necessary to fiddle around with the PRF in special situations, for example, if you have low flow. Now remember, we said that in the normal heart we have flow velocities which are below 1.5 to 2.0 meters per second. But since we have an aliasing border somewhere in the range of maybe 0.7 to 0.8, we have velocities, normal velocities in the heart, which also show at least some form of aliasing. So we have to just briefly discuss where we have fast and where we have slow velocities in the heart. We always have lower flow in the venous system. Therefore, we also have a low flow in the pulmonic veins and the inferior vena cava, as well as the hepatic veins, but also in the atria itself. And if we have a shunt, for example, between the left atrium and the right atrium, an ASD, the flow would also be lower. High velocities in the normal heart are usually found where there is some form of narrowing. So, across the valves, with the exception of the tricuspid valve, because the tricuspid valve is so large, the LVOT, the pulmonary arteries, and very often in a normal ventricle as well, if we have a hyperdynamic state. Here you can see aliasing both of inflow into the left ventricle, in the left ventricle, and also in the LVOT. So, all these can cause aliasing in a normal heart, at least to some degree. Many pathologies of the heart are characterized by high velocities, by jets. We can find them in the setting of stenosis, aortic, mitral, pulmonic, and also if we have regurgitation. Here's such an example where we have a jet which regurgitates back into the left atrium from the left ventricle. You can see aliasing, but the main color here is blue. Why? Because the jet is directed away from the transducer. And we also find jets, of course, if we have shunts, ventricular shunts, VSDs, but also a patent ductus and many other forms of shunts. The exception again, the atrial septal defect, which has a low velocity. Now, we already talked about two issues which are important in the way the color Doppler signal is displayed: the MAPS and the Nyquist limit. But there are many other factors which also influence the quality and also the sensitivity of the color Doppler information. And one is certainly the image quality. If you do not have a good 2D image, you will not be able to see the jets appropriately. So again, another reason to learn how to really image correctly. Here's an example. On the left-hand side, you see a patient who has a superb image quality. We can nicely see the aortic regurgitation jet and also the mitral regurgitation jet. Here on the right, a person where there's all sorts of color, but we cannot really determine what the problem here is. Why? Because the image quality is not good, but also for another reason. We do not have an optimal alignment between the ultrasound beam and the direction of the flow. In this case, we can see that we are perpendicular to flow, while here we are parallel, both to the aortic regurgitation and to the mitral regurgitation. Just as with two-dimensional imaging, the frame rate also plays an important role if we image jets. And so we have to aim for high frame rates if we use color Doppler. Now, the frame rate is determined by a number of factors. First of all, the scan line density, basically the quality of the transducer, and also where the emphasis is put. Most machines can kind of switch or change the emphasis between the 2D image and the color image. And so there's always a bit of a trade-off. Do you want to have a good background 2D image, or do you want to have a good color image and high frame rates? The sector width also plays an important role. Not only the sector width of the color box, but also the 2D image sector width. Why? Because what we're trying to have is a very high density of scan lines here within this region of interest. And if we're wasting these scan lines on other regions, and we're wasting processing power, then the quality and also the frame rate of the region that we're interested in is not going to be that high. Let me show you an example. In this image loop, we placed the color region of interest over the entire 2D image. Now, we're not only getting a very low frame rate of only 24 frames per second, we're even looking at regions where we can't expect any blood to flow, the tissue, so we have artifacts there. Now, we have a much smaller sector, the frame rate has increased, and we're concentrating more on the region of interest. And if we decrease the size of the sector even more, the frame rate increases to 84 frames per second, and then further to 132 frames per second. So this is where you should be imaging, just the region of interest, here in this case the mitral valve. Other factors that play a role for the frame rate of the color Doppler is the imaging depth and the pulse repetition frequency. But now it's time that we let Marion show us how we should adjust the settings if we perform color Doppler imaging.
Now I'd like to show you a little bit about the color flow. So you see I have my apical 4-chamber view here. I add the color. So principally every motion that goes to the transducer, any blood flow that moves towards the transducer will be colored in red. Color flow that moves away from transducer will be colored in blue. So how do we find the optimum setting? Basically it's the same like in the 2D image. You should focus on the thing you want to see. So don't make the color box, in example, very big. You see, when you make a very big color sector, you have a very low frame rate and the image doesn't look very nice. You may even oversee some very small and short insufficiency jets. So just make the color box as big as it's needed. The next thing is the gain settings. Be aware, when you undergain the color, you don't see any flow. You may miss a lot of information here. So increase the gain. There is a level where you get some noise inside the image, like here. So the best setting actually is when you have the noise, just reduce it unless you get rid of the noise, and then you know you have the best setting for your color flow, so you don't miss any information. Next thing would be the scale. You can even adjust the scale. In example, you want to measure some, or you want to see some low flow. Here, in example, the lung veins. You can even, in this patient, actually, it's quite good because it's a young patient, so the flow is not so low. But you may decrease a little bit the scale in order to get a nice flow in the lung veins where you have a little bit lower velocities here. And finally, when you have, for example, some insufficiency, which we don't have in this patient, so I can just only show you the principle, you could potentially move the baseline. When you have a mitral valve insufficiency, there is a special measurement called PISA, and there is a need for moving the baseline into another direction. You see here, you can do this in post-processing, so you don't need to do it in live scanning. Just move the baseline a little bit up. When you look, I just show it to you. When you look at this small area here, see, you move the baseline a little bit, and then you get better delineation of the area where you have to measure and where you have the aliasing.
In conclusion, I would like to show you that we can also use color Doppler in a different way. Not to encode the blood flow, but to encode the tissue. And this methodology is called tissue Doppler imaging. We already heard about tissue Doppler imaging when we talked about the Doppler techniques, and we'll hear much, much more when we talk about newer technologies and other technologies in echocardiography. But just to give you a brief overview of what tissue Doppler is good for, it's good for measuring the velocity of the myocardium and for assessing what we call deformation. In other words, displacement of the myocardium, strain, and strain rate. All of these parameters provide us with very important insights which relate to the function of the myocardium. Okay, so now we'll finally stop with physics and principles of ultrasound because, after all, I don't want you to fix a machine or build a machine, I just want you to use it. And now we'll come to a chapter which I think is also very, very important on how to image.